Hello, my name is Louis Charles Lamotte. My ZID is Z5600450, and here's my student ID. Today I will be talking to you about the experiment I have conducted titled The Understanding of the Solar System. First, we gotta define what are Kepler's law. Kepler's law are a bunch of laws that it tells us how planets move around the sun. The first law, called the law of ellipses, state that all planets move around the sun in an elliptical orbit, with the sun as one of the foci. The second law states that a planet sweeps out equal area in equal intervals of time. And the third law states that the square of the orbital period of a planet is proportional to its semi-major axis cubed, which is the formula written down there. Now let's proceed to question 9. Question 9A. There seems to be an obvious motion of the Earth oscillating at one point around its edge as the moon orbits it. And then the center of mass in scenario 1 is located within the sun, slightly closer to the sun's center of mass. And the center of mass in scenario 4 is located within the sun, slightly closer to the center of mass of the sun. And the last one, the center of mass in scenario 7 is located within the sun, at the center of mass of the sun. As there is no more gravity between Earth and the sun, the new system is only composed of the sun, and the center of mass will obviously be the center of mass of the sun, which is marked down there in red. The center of mass of the planet-moon system is slightly located at the edge of the Earth. This is due to the mass ratio of the planet-moon system being less significant than the sun-planet mass ratio. The sun-planet mass ratio has the sun moving around the barycenter. It is still oscillating at a barycenter, but those oscillations are very little. That's why it's not perceivable in the simulation. For my astronomical unit in this experiment, it's going to be 73,640,867 kilometers. I have chosen 4 different orbital distances and predicted using Kepler's third law their orbital period. Here are the prediction on the second column, and we can see that they're quite different from the actual orbital period. Why is that? Well, there are 2 main reasons explaining why it's not predicting 100%. First, there is a formula that I've used to calculate the orbital period. You just plug in for a planet distance and it spits out the orbital period for each one of them. The two main reasons explaining the margins of errors in Kepler's third law predicting the orbital period is that Kepler assumed that all planet moves in a perfect ellipse, but that is not true always. We can see that on the images in the next slides. We can see that it's not a perfect ellipse, so that assumption might not always be true, therefore might cause a miscalculation during the calculations. And the second main reason is the presence of the moon. If there are additional massive bodies influencing the orbit of the planet, such as the planet and the moon, the simple two-body assumptions of Kepler's law becomes less accurate, as will our calculations be less accurate. These perturbations can lead to variations in the orbital parameters. Here are some examples of the orbital distances chosen and their actual orbital period. Question 15. The planet in our solar system that will have the fastest orbital velocity is Mercury, and the planet in our solar system that will have the slowest orbital velocity is Uranus. This can be explained by combining 2 known equations, Newton's universal law of gravity and the centripetal force, which explain how planets orbit the sun. Combining these 2 equations, we get, solving for the orbital velocity, we get that the orbital velocity is given by the square root of the universal gravity constant times the mass of the sun divided by the orbital radius. So by this equation, we can see that as the orbital distance between a planet and the sun is shorter, the greater will be the orbital velocity, which is in Mercury's case, and as it's greater, the shorter will be the orbital velocity, which is why I will expect Mercury to have a faster orbital velocity and Uranus to have the slowest one, as it's the furthest one out there. In this experiment, I have learned the basis of planet, star, and planet-moon system of orbit, different parameters affecting orbit's velocity, period, and trajectory, and the validity of Kepler's law and its applications. How does a planet orbit the sun, and how does orbital period relates to orbital radius? Thank you for watching to the end.